So imagine yourself in the three-dimensional world of R3. You have the x and the y-axes, and the plane at the bottom, the z-axis is sticking up right here. One of the most important questions we're going to ask is, when we're given a bunch of different vectors floating around in three-dimensional space, and they might be behind the axes every now and then, they might be in front of the axes, but given all of these different vectors, the question will be, when are two vectors parallel, and when are two vectors perpendicular to each other? We're going to see that this is a question that's going to be useful to us over and over and over again. And so we're going to start answering this question in this module, and then we'll finish it up in the next topic down. So the first question, when are two vectors parallel? Imagine you had two vectors floating around in three-dimensional space. When would these two vectors be parallel? I mean, intuitively speaking, that would mean that if we were to run the lines that sort of pass through the tip and the tail, that these two lines would be parallel. But that seems like sort of a hard and kind of obscure thing to go and check. But that kind of an idea doesn't really use any of the cool vector properties. Remember that vectors can be translated around. So imagine we were to take this small purple vector and put his tail on the bottom of the orange vector. So I'd have a perfect copy of him right down here. Well, then what it would mean for these two vectors to be parallel is that one vector, the small guy, lives right on top of the other vector. In other words, these two vectors right here are scalar multiples of each other. The orange vector is simply a scaled version, a larger scaled version of the pink vector, or the pink vector is a smaller scaled version of the orange one. So, said differently, if you had a vector v who had components v1, v2, and v3, and a vector w who had components w1, w2, and w3, then the vector v is parallel to the vector w if and only if the vector v is some multiple of the vector w. I could even go a little bit farther. If lambda is a positive value, then v and w point in the same direction. Because one would be scaled up, like in this picture. If lambda was less than 0, if it was a negative value, then v and w would point in opposite directions. If one points north, the other would point south. Which of the following three vectors are parallel? So we could check this out in parts. Is v parallel to w? Well, we just have to see, is w some multiple of the vector v? Well, let's check this out. This would be the equation -6 minus 2, 4 equals lambda times 3, 1, minus 2. And remember that scaling is done component-wise, and so if we scale the right-hand side, we would have 3 lambda, 1 lambda, and minus 2 lambda. So this gives us three equations in one unknown. The first equation is -6 is equal to 3 lambda. The second equation is -2 is equal to lambda. And the third equation is 4 is equal to -2 lambda. Now, notice that the top equation has a solution lambda equals -2. The middle equation is lambda equals -2. And the last equation is lambda equals -2. And so this one scalar works on all three components. That tells me that is the vector v parallel to w? Yes, they're parallel. And in fact, they point in opposite directions. This is sometimes being called anti-parallel. Next, let's ask the question, is v parallel to z? Well, that would be the same thing as asking, is z some multiple of the vector v? So z is the vector 9, 3, minus 8. Is that lambda times the vector 3, 1, minus 2 for some magic value of lambda? Now, if we scale the right-hand side, we're going to get 3 lambda, lambda, and -2 lambda. And so that gives us three equations and three unknowns. The first equation is 9 is equal to 3 lambda. The second equation is 3 is equal to lambda. And the third equation is -8 is equal to -2 lambda. So if we solve this top equation, that gives me lambda is equal to 3. The second equation also says lambda is equal to 3, and the third equation says that lambda is equal to 4. Unfortunately, we can't use one lambda to scale all three components. And so that tells me, are these two vectors parallel? The answer is no. Lastly, is W parallel to Z? Well, you could check it out, but the answer is going to be no, because I know that W and V are already parallel. And since Z doesn't point in the same direction as V, it can't point in the same direction or the opposite direction as W. A more challenging question to ask is whether or not two vectors are at right angles to each other, whether or not they're perpendicular, or in sort of a strange bit of language, orthogonal. When we're talking about lines, we say perpendicular. For whatever reason, when we're talking about vectors, we say the magic word orthogonal. So given a vector v and a vector w, when are these guys at right angles? So first off, how would you even check something like this? Well, we could do what we did last time, which is we could translate this vector v so that its tail matches the tail of w. So we might have a perfect copy of v right here. That doesn't look very good. Let's try that again. We get a perfect copy of v right here. So how could we check whether or not the angle between these vectors, we'll call theta, is 90 degrees? How could you possibly test this? Well, notice that we're talking about 3 points right now. There's their common tail, there's the tip of w, and there's the tip of v. And if you're given 3 points in space, 3 points define a plane. There's a special plane that's running through these 3 points right here, and only these 3 points. So imagine we were to take this plane, however it's floating around in three-dimensional space, and look at it directly from above. Let's take a top-down view of this plane, whatever top-down direction it is, so that when I look at it, I don't see any sort of scaling. I just see a flat rectangular plane, and I see the common vertex point. There's the tip of w, and say here's the tip of v. And so there'll be the vector v is pointing this way. The vector w is pointing this way. And there's this unknown angle that we're trying to figure out right here. The nice part about this is that in the plane, once we have a specific plane in mind, you give me 3 points. Those 3 points describe a triangle. And the cool thing about triangles is that there is a very precise way of determining what the angle what one of the angles is if you know something about the lengths of the other two sides, and that's called the law of cosines. Let's hide all of the vectors and just consider this as a triangle for just a second. Let's say that we knew that the sides were A, B, and C. Now, if you happen to know 3 sides of a triangle, then you can work out the angle between any 2 of them by a formula from trig called the law of cosines. The law of cosines states this: the sum of the squares of any 2 sides of a triangle is equal to the square on the 3rd side of a triangle, plus an adjusting term of 2ab times the cosine of the angle between the 2 original sides. This is called the law of cosines. Now let's go put back our vector picture right here. We had a vector running along this bottom side, who we'd been calling w. And so the length of this base is nothing more than the length of w. So let's fill that in 2 spots in our equation. Here and here. Similarly, this second side was the vector we called v. And so the length of the second side of this triangle is nothing more than the length of the vector v. So we could fill that in 2 spots in our equation. Here and here. But what about the 3rd side of this triangle, the side C? Well, imagine I were to draw another vector in this picture, one who wasn't there originally. Say the vector who connects the tip of W to the tip of V. Right, that's a vector right here. It has a tail at the tip of W, and its tip is at the tip of v. But that's exactly one of our formulas right here. If you know the tail of a vector and the tip of a vector, then the vector who goes between them is the tip minus the tail. So the green vector we've just drawn is the vector v minus w. And so the length of the third side of this triangle is nothing more than the length of v minus w. So we've filled in the formulas for A, B, and C. Let's fill in the rest of the equation. Now let's focus on this first piece right here. We know that the vector w has components, and let's write the components as w1, w2, and w3. Then the length of this vector, the magnitude of w, is the square root of the sums of the squares of those, w1 squared plus w2 squared plus w3 squared. And so if we were to square both sides of this, we just get rid of the square root. And so this first expression right here is w1 squared plus w2 squared plus w3 squared. Similarly, the magnitude of v squared is v1 squared plus v2 squared plus v3 squared. And following along, since the components of the vector v minus w are the difference of the components of the vectors v and w, then v minus w quantity, or the length of v minus w squared, is going to be v1 minus w1 squared plus v2 minus w2 squared plus v3 minus w3 squared. Let me take that expression in green right there and expand it out. I'm just going to FOIL that whole expression out, and we're going to come up with a ginormous equation. So the left-hand side will stay the same, but the right-hand side is going to be, well, if we expand v1 minus w1 squared, that's v1 squared minus 2 times v1 times w1 plus w1 squared. If we expand v2 minus w2, that's going to be v2 squared minus 2v2w2 plus w2 squared. And if we expand out v3 plus w, or minus w3, we're going to get v3 squared minus 2v3w3 plus w3 squared. And then we have the rest of the equation. But now notice, on the left-hand side and the right-hand side, there are certain cancellations. There's a v1 squared on both sides of the equation, so we could cancel it out. And similarly, there's a v2 squared on both sides of the equation, so we can cancel that out. There's a v3 squared on both sides of the equation, so we can cancel that out. There's a w1 squared on both sides of the equations, so we can kill that. And a w2 squared on both sides of the equations, and a w3 squared on both sides of the equations. And so when we clean this thing up, we've canceled everything on the left-hand side. We just have a 0. And on the right-hand side, we have negative 2v1w1 minus 2v2w2 minus 2v3w3 plus 2 times the length of v times the length of w times the cosine of the angle between the vectors v and w. We could divide everything through by a 2, which just means we get rid of these coefficients, and move these three terms over to the left, and we'll be left with the following equation. v1w1 plus v2w2 plus v3w3 is equal to the length of v times the length of w times the cosine of the angle between them. And believe it or not, this formula here is what we're looking for. In fact, the expression on the left is so important that we're going to give it its own special name. If a vector v has components v1, v2, and v3, and the vector w has components w1, w2, and w3, then we're going to define the following symbol, v dot w, to be the formula v1, w1 plus v2, w2 plus v3, w3. And we're going to call this the dot product of v and w. So the dot product of two vectors is the sum of the pairwise products of their components. So for example, if we had the vector 1, negative 3, 2, and we had the vector 4, 3, 1. Then their dot product would be the product of their first components, 1 times 4, the product of their second components, negative 3 times 3, and the product of their last components, 2 times 1, added together. That is, get us a grand total of 4 minus 9 plus 2, or 6 minus 9, or minus 3. And so the dot product of these two vectors would be minus 3. The most important fact about this dot product was what we had just shown in the previous example, that v dot w, this formula up here, is always equal to the length of v times the length of w times the cosine of the angle between the two vectors. This is sometimes called the dot product law of cosines. One of the most useful things about this is it gives us a way of checking on the angle between vectors. And how it works is it works like this. Just focus on the right-hand side of this equation. Now the length of v is always going to be a positive value, and the length of w is always a positive value. But the cosine of an angle could be positive or negative. In fact, if we make a quick sketch of the cosine curve, here's the cosine curve. So this is at pi, this is at pi over 2, this is at 0. Well, imagine if you're talking about the angle between two vectors. Here's a vector here, here's a vector here. The angle between them should range between 0 and 180 degrees. So we're only looking at this much of the graph. Well, this much of the graph is positive, so cosine of theta is positive, as long as theta, the angle, stays between 0 and less than pi over 2. The graph is negative down here, so we're going to know that the cosine of theta is negative if theta is larger than pi over 2, but smaller than or equal to pi. And the graph crosses the x-axis right here at theta equals pi over 2, so the cosine will be theta, if theta is pi over 2. In other words, the sine of the right-hand side of this equation is completely determined by the angle between the vectors. In other words, v dot w is going to be positive if the angle is acute, between 0 and 90 degrees. It's going to be negative if the angle is obtuse, larger than 90 degrees but smaller than 180, and it's going to be 0 if the angle is a right angle. And so this gives us a fantastic way of checking whether or not two vectors are at right angles to each other. Let's take a look at an example. Which of the following vectors are orthogonal? Well, we could ask this question right here. Remember, orthogonal is just the vector synonym for perpendicular. So we could ask the question, is the vector v orthogonal to w? Well, to do that, we just work out their dot product. And the sign of their dot product will tell us. So we're going to take the vector 1, minus 2, 3, and we will dot it against the vector 1, 1, 2. So remember the dot product, we'll take the product of the first components, 1 times 1, the product of the second components, negative 2 times 1, and the product of the third components, 3 times 2, and we'll add them up. So that will get us a grand total of 1 minus 2 plus 6. That's 7 minus 2, which is 5. So this is positive. Since this value is positive, it tells us that these two vectors are not orthogonal, but that the angle between them is acute. All right, let's take a look at v and z. We could ask, is v orthogonal to z? Well, let's just check their dot product. So we'll take the vector 1, minus 2, 3, and we'll dot it against the vector 2, minus 2, minus 2. So when we take the product across the first rows, we get 1 times 2. The product of the second components is negative 2 times negative 2, and the product of the third components is 3 times negative 2. And then we'll add these three values up. So that's going to get us 2 minus minus 4 minus 6. That's going to get me 6 minus 6, and that gets me 0. Since 0 is neither positive or negative, that tells me that these two guys right here are in fact orthogonal. So the answer to this question is yes. What about W and Z? Is it the case that W is orthogonal to Z? Well, let's do one last dot product. We'll take 1, 1, 2, and we'll dot it against 2, minus 2, minus 2. So the product across the first rows is 1 times 2, across the second rows it's negative 1 times 2, and across the third rows it's 2 times negative 2. That'll get me 2 minus 2, which is 0 minus 4, which is negative 4. That value would be negative, and so that tells me that these two vectors are not orthogonal, but that the angle is obtuse. So this example shows that we can now answer the question posed at the beginning of the podcast efficiently. That two vectors are orthogonal if and only if their dot product is 0. It turns out that this dot product law of cosines has some other interesting applications as well. For example, the dot product can be used to compute lengths of vectors. Just take the dot product law of sines and replace W with V. We would have V dot V is equal to the length of V times the length of V times the cosine of the angle between V and V. Well, since these two are the same vector, the angle between them is 0. The cosine of 0 is 1, and so this tells us that V dot V is equal to the length of V times the length of V squared. So we have a useful formula right here, that the length of a vector is the square root of its dot product with itself. This just gives us another alternative way of memorizing or of reproducing the magnitude of a vector. We can also solve this equation for the angle theta. If we were to go and divide both sides by these lengths here, we would get that the cosine of theta is equal to V dot W divided by the length of V times the length of W. So we could go and apply the inverse cosine. We would get theta is equal to the arc cosine of V dot W over the length of V times the length of W. Now, when we were doing spherical coordinates and cylindrical coordinates and polar coordinates, we had to be careful when we pulled out these inverse trig functions. But remember that the angle between vectors is always something between 180 degrees, that's the worst case it could be, and 0 degrees. So the angle is always between 0 and 180 degrees. But the arc cosine always gives angles between 0 and 180 degrees. And so in this case, no correction is necessary. This is the exact formula for the angle between two vectors. So for example, if we had the vector 1, 0, 3, and we had the vector minus 1, 1, 2, then the angle between these vectors would be the arc cosine of their dot product. So their dot product would be 1 times minus 1 plus 0 times 1 plus 3 times 2, which is 6, divided by the length of the first vector. Now the length of the first vector is the square root of 1 squared plus 0 squared plus 3 squared times the length of the second vector. The length of the second vector is 1 squared plus 1 squared plus 2 squared. So we get theta is equal to the arc cosine of 5 on the top, and on the bottom we have the square root of 10 times the square root of 6. Or the arc cosine of 5 over the square root of 60. Now, more often than not, we're not going to be able to work out this angle precisely, but if we have a calculator, then we could crank it out on a calculator. And in this case, we would find that theta is approximately 50 degrees. One final application of the dot product law of cosines is what's called the projection problem. The projection problem says this. Suppose you have a vector v, and then you have some other vector. Let's call it w. The projection problem is this. Is it possible to write the vector v as a sum of two vectors, one of whom is parallel to W. This is sometimes called V parallel. And one of who is perpendicular to W, which is sometimes called V perp. In the special case of W being the vector I, we've seen that this is always possible. Every vector can be written as a multiple of I, AI, and then a multiple of a vector perpendicular to I, Bj. So this is simply a generalization of this idea of a standard basis, the vectors who run east, west, north, south, to any potential basis. You give me a direction, could we write any vector in terms of a piece parallel and perpendicular to it? Believe it or not, there's an easy formula for this. We've got the vector v and we've got the vector w. Now imagine we were to go and draw a line all the way through the vector w, and we're going to turn this picture into a triangle. So we'll have a right triangle whose base runs along this line right here. If the angle between these two vectors is theta, then the length of this side right here would be the length of the hypotenuse times the cosine of that angle by basic trigonometry. This is the adjacent side, that's the hypotenuse. So if we could find a unit vector who pointed in the same direction as w, I'll call him u, then we could take this unit vector u, we could multiply him by the value length of v times the cosine of theta, and this would be exactly the parallel component. It would be exactly this vector right here, because it would have exactly the right length and it would be pointing in exactly the right direction. But remember, if we have any vector whatsoever, we can find a unit vector who points in the exact same direction by taking the vector and dividing by its length. And so this gives me the following formula. The parallel component of a vector is the length of the vector v times the cosine of the angle between the vectors divided by the length of that vector times w. Alright, I said there was an easy formula. This by no means looks easy, but here's the clever bit. Let's multiply the top and bottom by the length of w. We're just multiplying the entire expression by 1, so we haven't changed anything. On the bottom, the length of w times the length of w, that's the length of w squared, which is just the dot product of w with itself. And on the top, we've got the length of v times the length of w times the cosine of the angle between them. Well, that's just the vector, or the dot product law of cosines. This is just v dot w. And so this becomes our new and improved formula. So the vector component of v parallel to w is a multiple of w, and the multiple is v dot w over w dot w. In fact, this formula right here is sometimes called the projection of v onto w. So now we figured out the parallel side. But what about the third side, the side running perpendicular to these? Well, we could run through another round of trigonometry, and that's fine. Be my guest. Have oodles and oodles of fun. But just notice one thing about this perpendicular component. It goes from the tip of v parallel to the tip of v. Whenever you have a vector who goes from one point to another, it always takes the form of the tip minus the tail. And so now we can go and compute the two components. The parallel component of v onto w, and the orthogonal component of v on w. Let's just try this out on a specific example. Compute the parallel and orthogonal components of the vector 1, 3, 2 on the vector 4, minus 1, 3. So part of figuring this thing out is knowing who's who. We want to find the components of this vector, which means this is the guy who's playing the role of v. And we want to find them on this vector. So that means that this guy right here is playing the role of w. So now we can just go and use our straight up formulas right here. We know that the parallel component, v parallel, also called the projection of the vector v onto the vector w, is going to be v dot w over w dot w, this multiple times the vector w. Right? It's supposed to be parallel to w, so it has to be a scalar multiple of it. So let's fill in all of the details right here. We know that v dot w would be the vector 1, 3, 2 times the vector 4, minus 1, 3, dotted with it, sorry. So we'll dot across the top rows. 1 times 4 is 4. Then we'll add the next element. 3 times minus 1 is negative 3. And then we'll add the third products, which is 6. And so that gets me 10 minus 3, which is 7. On the bottom, we're going to have the vector w dotted with itself. So 4, 1, minus 3, dotted with 4, 1, minus 3. So 4 times 4 is 16. 1 times 1 is 1. And minus 3 times minus 3 is 9. And that's going to get us a grand total of 26. And so this is going to be 7/26 times the vector w. 4, minus 1, 3. And so we're going to have, multiplying this fraction through, 28/26, negative 7/26, and 21/26. This is maybe the one problem with writing things in columns, is it doesn't handle fractions very well. It's not particularly forgiving, so I'll also write it in rows just to make it a little bit easier to read here. 28/26, negative 7/26, and 21/26. Now that we've got that, we can work out the orthogonal component, not vt, v perp, the orthogonal component by taking v and subtracting the parallel component off of it. So the vector v is the vector 1, 3, 2, and the orthogonal component, or sorry, the parallel component is what we've just found, 28/26, negative 7/26, and 21/26. And so if we do that subtraction, reading across the rows, we're going to have 1, which is 26/26, minus 28/26. The second row is 3, which is the same thing as 78/26, minus negative 7/26. And then reading across the bottom row, we're going to have 2, which is 52/26, and we will add, or subtract, from that 21/26. And so if we clean this thing up, the first component is going to be 26/26 minus 28/26, or negative 2/26. The second component is 78/26 plus 7/26, which would be 85/26. And the third component is 52/26 minus 21/26. Whew, that's tough to say, which would be 31/26. And so here we have the two components we're looking for, the parallel component and the orthogonal component. A useful thing that we could do at this point, by way of checking our work, is that these two vectors should in fact be, well, perpendicular to each other. And so we could do a quick check on our work by simply double-checking their dot product. So let's test this out really quickly. Let's take 28/26, negative 7/26, and 21/26, and dot that against negative 2/26, 85/26, and 31/26. Multiplying across the top, we'll take 28/26 times negative 2/26. So multiplying the numerators, 28 times negative 2 would be negative 56. 26 times 26 is 676. Next, we'll add the next two products. 7/26 times 85/26. Now negative 7 times 85 is negative 595. 26 times 26 is 676. Finally, we'll take 21/26 times 31/26. So the bottom is 676. The numerator, 21 times 31, is 651. So since all these have a common denominator, we're going to have a common denominator of 676. Negative 56 minus 595 is negative 651 plus 651, which gives us a grand total of 0. So in fact, the parallel part and the orthogonal part are orthogonal after all. Now we've been focusing all of our attention in R3, but it's worth pointing out that the dot product makes complete sense for any two vectors in R2. If we had a vector v and a vector w, then it makes sense to dot these two guys together. If the vector v had components v1, v2, and the vector w had components w1, w2, then v dot w, their dot product, would just be, well, let's see, we'd have v1, v2 dotted against w1, w2, and sort of doing what we did in R3, we'd multiply across the top row to get v1, w1, we'd multiply across the second row to get v2, w2, and then we'd add these together. And so this is the dot product in R2. Everything that we learned about before still counts in R2. For example, the dot product is still going to be the length of v times the length of w times the cosine of the angle between these guys. Maybe the easiest way to believe this is that all R2 is, oops, forgot the little 2 there, is it's just the bottom plane in R3. So if we were to think of these vectors as vectors in R3, we'd really just be adding a 0 component right here, and so the dot product would have included an extra 0. So everything that we proved in R3 is therefore true in R2. Let me just give one sort of neat example of the dot product in R2 that you're familiar with, but you may not know the reason behind this. And it's this idea right here. Imagine that you have two lines. So say you have this first line right here, which has the form y equals mx plus b. And then imagine you had a second line right here, which took the form that is not very linear at all. Let's try that again. That looks more like a line. Y equals nx plus c. So suppose you had these two lines right here. Then one of the facts we've been taught is that these two lines are perpendicular if and only if there was a condition on the slopes. And hopefully you remember this condition was that the slopes were opposite reciprocals. So n has to be the reciprocal of m and the opposite in sign. But why is this true? Well, maybe the easiest way to show you why this is true is to use vectors. So let me just put a single tick mark right here at 1 unit. So what I'm going to do is I'm going to identify a vector on this first line. Let me start here where it crosses the x or the y-axis, and I'll go 1 unit over, and I'll look at this arrow right here. So this is a vector that I'm pulling off of this first line. Now it's a vector whose tail is at the point 0, b, because it's the y-intercept. Sorry, its tail is at the point 0, b. And then he's gone over 1 unit, so this would be the point 1, comma. If I plug 1 into my equation, I would have m plus b. So since I know the tail and I know the tip, I know what this vector is. This vector is going to be, well, its x-coordinate increased by 1, and its y-coordinate went from b to m plus b, so its y-coordinate increased by m. And so that's this vector right here. Now if we were to do the same thing, start at the y-intercept, go 1 unit over, and identify this vector right here, then this vector is going to be 1n. Another way of thinking about that is, well, he went 1 unit over. How far does he drop down? Well, isn't that exactly what the slope is supposed to measure? How far you rise or fall when you move 1 unit over? So, two different ways to get to the same endpoint. So how do these vectors help us prove this statement? Well, let me go and add a couple of auxiliary lines to it. These two lines right here are going to be perpendicular. That's the same thing as saying that these two vectors are going to be perpendicular. The vector 1m and the vector 1n. Because these vectors, well, I've drawn them right here, are parallel to the two lines. So if the vectors are perpendicular, the lines are perpendicular. But we know that the vectors are perpendicular if and only if their dot product is equal to 0. So if we dot them, when we multiply across the first row, we get 1. When we multiply across the second row, we get mn. And if I were to solve this for n, I would get mn is equal to 1, or n is equal to 1, negative 1 over m. And that's what we wanted to show.